Okay, we're going to learn how to calculate delta H, which is the change in enthalpy, using this new equation. Delta H is equal to the sum of bond energies broken minus the sum of bond energies formed. This symbol is sigma, which means sum. So first of all, before I do some examples, I want to give you a little bit of background as to why we're doing broken minus formed. Remember, in our energy path diagrams, we have our reactants with some amount of potential energy, and then our products with some amount of potential energy. And the difference between products and reactants gives us our delta H, which is our change in enthalpy. And if products land lower than our reactants, we have an exothermic reaction. If products land higher than our reactants, we have an endothermic reaction. But remember, in order for our reaction to proceed, the bonds of our reactants have to be broken. So that's why we always have activation energy. Okay, our reactants must gain some amount of energy to reach that activated complex. This represents the bonds being broken. Energy is absorbed to break bonds. So energy goes up, energy is taken in to break the chemical bonds. And then once we start to make bonds, okay, as we make bonds of our products, energy is released. And this holds true for any type of reaction, whether it's endo or exo. As products are being made, energy is released. And the sign here tells us that when bonds are broken, energy is absorbed. That's why it's a plus sign in front of the broken. And when energy is released, we signify that with a minus sign. So energy is leaving the system. So we do broken minus formed. So let's take a look at some examples. So number one, I calculate delta H for hydrogen plus fluorine yields hydrofluoric acid. First thing I need to do is draw a Lewis structure to see what bonds are broken and what bonds are formed. So real quickly, I would draw hydrogen, fluorine yields 2 HF. Okay. So using my formula, bonds broken minus bonds formed, I have one hydrogen to hydrogen single bond being broken and one hydrogen to fluorine, fluorine to fluorine single bond being broken. So I'm going to use this data table above, and these are not numbers that I need to memorize. I will be given these values on tests and quizzes, and you'll have this available for homework assignments. So I'm looking for this bond right here, hydrogen to hydrogen single bond. It has a value of 432 kilojoules per mole. So for every 1 mole of hydrogen to hydrogen single bonds, it requires 432 kilojoules to break that bond. So my delta H is going to be equal to 492. Okay. And then I'm looking for my next bond, fluorine to fluorine single bond. And that has a value of fluorine to fluorine right here, 154 kilojoules per mole. So I add that. There's the sum of my broken. And now we're going to subtract out the sum of our bonds being formed. Okay, so minus, what bonds are we making? We're making a hydrogen to fluorine bond, but there are 2 of them. So I'm going to have to multiply my HF bond by 2. So my HF bond is 565. So we're going to subtract 2 times 565. Okay. And I'm going to do this math. Delta H equals 586 minus 1130. I get negative 544 kilojoules per mole. And since we're dealing with delta H, it'll be mole per reaction. Okay. For letter B, we're going to repeat the process. Draw a Lewis structure to see what is being broken and to see what is being formed. So I have H to H plus chlorine to chlorine yields 2H to Cl. Okay. Why don't you go ahead and pause the video and you try this one on your own and then come back and see if you get the correct answer. Okay, so in letter B, I have one hydrogen-hydrogen bond being broken, one chlorine-chlorine bond being broken, so I add their two bond energy values together, and I get 671, and then I'm going to subtract out the bond energies of the hydrogen-chlorine bond, which is 427, multiply that by 2, because it's a coefficient of 2, and in the very end, I get a delta H of negative 183 kilojoules per mole of reaction. For letter C, I'm going to start the same way, draw my Lewis structure. I'm going to do that. This is what I end up with. I got a triple nitrogen to nitrogen bond, single hydrogen to hydrogen, and then in ammonia, I have 3 nitrogen to hydrogen bonds. The process is still the same. I'm going to take my broken. Okay, so I have a broken here. I'm looking for a nitrogen to nitrogen triple bond being broken. I'm looking for its bond energy value. And it has a value of 941. So delta H, 941. Its coefficient is 1, so I don't have to multiply it. I'm looking for hydrogen to hydrogen again, which I've already used before. That has a value of 492, but there's a coefficient of 3, so I need to multiply it by 3. So plus 3 times 492. All of that, okay, gets added together. Subtract out your bonds being made. This is why you need to draw Lewis structures. I see I have 1, 2, 3 nitrogen to hydrogen bonds here. Okay, but this coefficient of 2 means I have 2 times 3 nitrogen to hydrogen bonds. So really I have 6 nitrogen to hydrogen bonds being broken here. So I'm going to do 6 times the bond energy of nitrogen to hydrogen, single bond, and to H, which is 391. So insert 391. So 6 times 391. That's the sum of all the bonds being formed. And so my delta H ends up being 2237 minus 2346. And I get an overall delta H of negative 109 kilojoules per mole of reaction.